Red dot sight. Red dot sight traces to early 20th century reflector concepts and matures in the mid-1970s with the aim-point electronic designed by Helsingborg engineer Jan Arne Ingemund Ekstrand and launched by Aimpoint AB in 1975. It begins as a civilian and military solution for faster target acquisition and later enters U.S. service at scale with the M68 Close Combat Optic designation for the Comp M2 2000. That path establishes the template for modern non-magnifying reflex devices on fighting rifles, carbines, and pistols. Optically, a red dot uses an LED positioned at the focal point of a curved, partially silvered mirror. A dichroic coating reflects the emitter's narrow band, typically around 670 nanometers, while transmitting much of the rest of the spectrum, so the reticle appears bright over a relatively neutral scene. The dot stays aligned with the bore regardless of modest shifts in eye position. Practical parallax diminishes with distance and is functionally negligible at longer ranges. Variants split into enclosed tube bodies and open frame designs, with some optics adopting Mansion or two-lens correction to tame off-axis aberrations. Magnification is a true 1x and encourages both eyes open shooting with minimal distortion and a field of view defined mostly by window size rather than optical constraints. Construction trends toward aluminum or polymer housings, nitrogen purging, waterproof sealing, and shock-resistant electronics. Multi-layered dielectric coatings reduce glare and keep color cast modest. LED power demands are low, and modern models operate for extended intervals on a single cell, measured in many thousands of hours when left at conservative brightness. Brands and models span Aimpoint's line from the original electronic through the Comp M2, M4, Micro T2, and Acro P series, along with Trigecon's RMR family, Holosun's enclosed and open emitters, Sig Sauer's Romeo line, Vortex's compact dots, and Leupold's Delta Point Pro. Early emitter flicker and battery contact complaints are largely historical. Improved spring geometry and vibration resistance have reduced those issues. Competitive shooters in IPSC and 3-gun, hunters in dense cover, and military users in close quarter settings report fast acquisition and repeatable zero when mounts are torqued properly and kept on the receiver rather than the handguard. Reticles commonly range from roughly 2 to 5 minutes of angle, with smaller dots favoring precision on small targets and larger dots aiding speed and visibility in bright light. Holographic sight. Holographic sight arrives in the 1990s as the distinct branch of reflex technology. EOTech develops the design and introduces it to the civilian market at the 1996 SHOT Show under the Bushnell HoloSight label before fielding military variants. The concept replaces the LED mirror arrangement with a laser-illuminated transmission hologram recorded in a thin film integrated into the viewing window. A laser diode passes through the film and reconstructs the reticle as a three-dimensional hologram that appears at a set distance, commonly around 100 yards. That focal placement lets the shooter concentrate on the target plane rather than the sight body, which supports both eyes open technique and quick reticle-to-target alignment. EOTech's grading system compensates for temperature-induced wavelength drift in the diode, keeping the point of aim stable across environmental changes. Parallax error falls with distance and is essentially negligible at the set hologram range. At very close distances, apparent reticle shift remains bounded by the sight window. Magnification is natively 1x, but holographic units pair well with flip-to-side magnifiers when mid-range identification is required. Clear transmission through the holographic window reduces tint and color bias relative to many reflective dots. Construction typically uses multi-layer glass windows in a sealed aluminum or reinforced polymer shell rated for impact and environmental exposure. The trade-off is power. Laser diodes draw more current than LEDs, so runtime is measured in hundreds or low thousands of hours rather than many tens of thousands of hours. EOTech's EXPS, XPS, and 512 families dominate the category, with Vortex entering with the Razer AMU H1 and its Gen 2 refinement. Thermal imaging scope. Thermal weapon sights originate in military programs and later spread to civilian markets as sensors shrink and costs fall. They form images from long-wave infrared radiation rather than visible light, so the optic detects heat differences and presents them on a microdisplay with an overlaid aiming reticle. An infrared transparent objective focuses energy onto a microbolometer, often VOX or similar,
whose output the processor converts to a thermogram. The user views the processed scene on an internal OLED or AMOLED screen with selectable color palettes. Sensor resolution, pixel pitch, and refresh rate determine much of the practical performance. Examples in testing include 640 by 480 at 17 microns, 400 by 300 arrays, and 384 by 288 sensors, with refresh rates around 50 Hz for smoother panning and tracking, and lower rates at the value end. Detection and identification distances vary with target size, ambient contrast, and optics, with top units reporting long detection ranges and more modest distances for confident identification. Magnification is typically digital and variable, ranges such as 1 to 6x, 1 to 8x, or 2 to 16x, and high digital zoom can introduce pixelation. Construction emphasizes sealing, shock resistance, and battery management. Ratings such as IPX7/IP67 are common, and some units advertise shock survival in the hundreds of G with tests on 223, 308, and Magnum rifles. Battery life is a recurring constraint, often several hours per pack, and declines in cold weather and when recording or streaming video. Interfaces add features such as picture-in-picture, multiple zeroing profiles for different rifles, onboard recording, app connectivity, and ballistetic integration. Brands frequently cited include Pulsar's Thermion series for high image quality and robust build, Burris's for durable hunting-oriented units with strong shock ratings, ATN's Thor 4 line for feature density and long runtime, and SIG's Echo series tuned for quick close-range work with lower refresh rates. Zero retention after repeated firing and environmental swings is part of most protocols, with reports of stable zeros over multi-month use. Thermal excels at night on hogs and predators, in smoke or fog where visible light struggles, and for surveillance.
Night vision scope. Night vision technology predates the Second World War, with early active infrared systems fielded by Germany and the United States, and develops rapidly in Vietnam with passive first-generation tubes. Post-war commercial work by figures such as Vladimir Zworykin at RCA contributes to the civilian side, and modern production rests with manufacturers of image intensifier tubes and assembled devices. The core mechanism converts incident visible and near-IR photons to electrons at a photocathode, multiplies them through a microchannel plate, and converts the amplified electron image back to visible light on a phosphor screen. Generational changes define capability. Gen 1 brings passive operation but modest resolution and edge distortion. Gen 2 introduces the microchannel plate and raises gain substantially. Gen 3 uses gallium arsenide photocathodes and ion barrier techniques to improve sensitivity and service life, with later refinements such as auto-gating to maintain image quality under sudden light changes. A commonly referenced performance metric multiplies line pairs per millimeter by signal-to-noise ratio. Export control regimes consider that figure when determining what may be shipped abroad. Form factors include weapon-mounted scopes, helmet monoculars and binoculars, clip-on units in front of daytime optics, and dedicated long eye relief systems. Weapon-mounted examples in civilian channels include digital day-night scopes that use sensors and screens rather than tubes, such as ATN's X-Sight, and dedicated Gen 3 auto-gated devices from companies such as AGM. Digital units offer high magnification ranges and color palettes with shorter battery life. Tube devices provide superior low-light performance with careful handling to protect against bright light exposure. Variable power scope. The variable power scope emerges in practical form in the early 20th century, with Zeiss among the pioneers, and achieves broad hunting acceptance by the mid-1960s as manufacturing and sealing improve. The optical principle is straightforward. A cam moves an internal erector assembly to change magnification, with the reticle positioned either in front of that group in the first focal plane or behind it in the second focal plane. First-plane reticles keep hold values constant across the zoom range. Second-plane reticles preserve a familiar sight picture, but expect the user to know at which power the subtensions are valid. Classic ranges such as 3 to 9x, 4 to 12x, and 2.5 to 10x cover general hunting, while 4 to 16, 6 to 24, and beyond address precision and mountain applications. Modern multi-coatings substantially close the brightness gap that once favored fixed powers. Small, well-built variables can rival older fixed scopes in low light, despite having more glass in the path. Mechanical quality governs durability under recoil. Large, heavy variables on hard-kicking rifles stress erector tubes more than compact models, and careful selection avoids unnecessary mass. Variables dominate the consumer market because they combine versatility with reliable mechanics and coatings that the first generations lacked. They also form the base technology from which LPVOs evolve. LPVO. The LPVO grows out of a need to bridge the speed of a reflex sight with the reach of a scope on modern carbines. It is a conventional rifle scope engineered to deliver a true 1x at the low end and a modest upper limit of magnification for mid-range shots. The image passes through an erector system rather than being projected, so even true 1x feels subtly different from a red dot. But the result is fast enough for most close work while enabling observation and precision farther out. Magnification ranges cluster around 1 to 4x, 1 to 6x, 1 to 8x, and increasingly 1 to 10x. Throw levers on the power ring are common to facilitate quick changes between near and far stages. Optical layout may place the reticle in the first focal plane, allowing consistent hold values across the zoom range, or in the second focal plane, preserving a constant-size aiming picture that many hunters find familiar. Each choice brings trade-offs in perceived reticle thickness and eye box forgiveness at the extremes. Compared to a red dot, an LPVO introduces some tunnel effect at low power and enforces eye relief limits. But the etched reticle remains visible without illumination, which preserves functionality if the battery is off or depleted. Brands noted in the field include Vortex's Razor Gen 3 1 to 10x and Venom 1 to 6x, Nightforce's NX8 1 to 8x, and options from Leupold, Steiner, Bushnell, and Primary Arms.
Smart or ballistic computing optics. Connected and computing optics integrate sensors, processors, and displays with conventional sighting systems. The principle is to overlay a ballistic solution on the observed scene after the optic and its associated devices gather range, inclination, atmospheric conditions, and user-defined ballistic data. Implementation ranges from traditional glass with a heads-up overlay to digital day-night platforms that render the entire scene on a microdisplay. Representative systems include Swarovski's DS, which merges premium glass with an on-screen ballistic correction, Revic's PMR concept that links optic and app, and SIG's BDX ecosystem that uses a rangefinder to feed solutions to a scope. Eliminator-type units incorporate onboard ranging and compute a hold point in the sight picture. The success of these systems depends on accurate inputs, muzzle velocity, ballistic coefficient, zero data, and on environmental readings. Incorrect entries or poor ranging yield incorrect solutions regardless of optical quality. Construction follows the parent platforms, sealed housings, coated lenses where applicable, and electronics designed for recoil resistance. Battery life is finite relative to passive optics, and firmware updates add features or correct behaviors over time. Technological advantages include faster, more repeatable holds without manual dope cards and the ability to synchronize profiles across rifles.
Prism sights. Prismatic sights draw from late 19th century binocular engineering and early 20th century rifle applications. Warner and Swazi's prismatic scopes appear on U.S. M1903 sniper rifles in the First World War, with thousands produced. Construction of those early units uses steel and brass with internal blacking, delivering roughly 5 to 6 power and a narrow field of view by modern standards. The prismatic pathway persists and, in the contemporary era, yields compact, fixed-power combat optics typified by the Trijicon ACOG and the Elcon family. The defining features are a short optical train that uses a prism for image erection and an etched reticle placed within the optic. The etched reticle remains visible without power and accepts illumination for low light. Because the reticle exists in glass rather than as a projected emitter, shooters with astigmatism often perceive a crisp aiming point and detailed ballistic markings. Typical magnifications sit at 1x, 2x, 3x, 4x, and occasionally 5x, with some designs, such as the Elcon Spectre DRT, offering switchable or variable states. Prism sights impose eye relief requirements and carry more parallax than red dots. They are, however, compact and mechanically robust, with excellent retention of the aiming reference even if electronics fail. Common use places them on patrol rifles, designated marksman configurations, and carbines where a stable etched reticle, compact size, and an illuminated daylight visible reticle are desirable. Fixed power scope. Fixed power scopes persist alongside variables because simplicity offers benefits in weight, ruggedness, and light transmission. The contemporary landscape includes both traditional refracting designs and prismatic combat optics. Civilian examples include compact scout scopes such as the Burris 2.75x, which provide extended eye relief for forward mounting, simple duplex reticles, and very low mass. On the combat side, the Trijicon ACOG family becomes emblematic. A 4x32 with tritium and fiber optic illumination that requires no batteries, multi-coated lenses, and a housing proven across harsh environments. Other fixed options include Primary Arms SLX Prism series in 1x, 3x, and 5x with long-claimed battery life for illumination and etched reticles that remain useful without power. SIG's Bravo 3 targets a similar role with a 3x fixed magnification and integrated mounting. At the precision end, dedicated 10x scopes, such as the US Optics FD-NFX10, and focus on repeatable mechanics over zoom flexibility. Fixed designs excel where roll clarity exists. Fast carbines that benefit from a bright, simple sight picture, scout rifles that demand generous eye relief, and long-range rifles that prioritize a consistent reticle scale. Reports emphasize zero retention under recoil and the advantage of an always-there reticle in austere conditions. The trade-off is, by definition, a single magnification, which places a premium on matching the optic to the mission and on adding an auxiliary microsight if immediate close-range use is part of the profile.
Flip-to-side magnifier. The flip-to-side magnifier develops as a way to extend the reach of red dots and holographic sights without discarding their speed at 1x. The configuration keeps a 1x primary optic up front and mounts a fixed power magnifier behind it on a pivot or flip-to-center mechanism. When needed, the magnifier drops into line to provide 3 power and increased target discrimination. When not, it swings aside and returns the system to a 0 magnification sight picture. The magnifier contains no reticle. It simply enlarges the projected reticle and target. Common magnification is 3x with occasional higher options. Eye relief is shorter than on most scopes and must be managed carefully. Figures around 2 to 3 inches are typical. Field of view varies by model and influences how quickly the shooter can acquire targets through the stacked system. Diopter adjustment allows the user to tune focus. Durability and return to 0 after flipping are recurring themes in evaluations, with higher-end mounts designed to center the optical axis reliably on repeated transitions. Representative equipment includes the EOTech G33, Holosun's HM3X paired with the HS510C red dot, Sig Sauer's compact Juliet 3 Micro, and budget-minded options such as UTG's 3X with flip mount. Field testing often covers grouping at 50 to 200 yards, observed point of impact shift when the magnifier is introduced, and handling under rain and temperature changes. Benefits include instant movement between 1x and 3x and the ability to positively identify small targets at intermediate ranges. Though the assembly adds weight, occupies rail space, and imposes the eye relief limits that red dots normally avoid.
We appreciate you watching. If you found the video informative, consider sharing it with others who enjoy firearm history and design. Suggestions for future topics are always welcome in the comments.